We're going to take a more quantitative look at the motional EMF that we talked about last time. So we're going to revisit our system where we have a long wire, we've got a rod connecting the wires, the rod is free to move, we've got a light bulb. This time we're going to make it horizontal just so it's a little bit simpler. We don't have to deal with gravity. And we're going to say that this rod has some velocity to the right. Now that may be caused by whatever, maybe it's my hand pushing it. But regardless, we're going to say that the rod is moving to the right. Now we know that magnetic flux is equal to the B field times the area times sine theta. Unless it's cosine theta. Anyway, we know that the flux is at a maximum. I forget which way, whether theta is defined as an angle from the normal in this case or an angle from the surface. Either way, that the flux is maximum when that B field is perpendicular to the area, and so we don't need to worry about whatever trig function goes there. Yeah, so I guess it would be cosine theta because I think that angle is from the normal to the surface. Anyway, but regardless, the flux we can still say is the B field times the area in this case because it's just perpendicular to that area. So a change in flux, in this case, we have a constant B field, so it's B times a change in area. Okay. Well, this area, if we call the length of this rod L, and I'm going to make that a script L because we're going to use something called capital L later, and we're going to use I for current. So that area is just a length times a width. Okay, but that width is changing, so our delta A is BL delta width, and it's changing at a rate of VT. You know, this width here is changing as the rod moves over, and the rod covers distance of V times T. All right. So Faraday's law says that our EMF has a magnitude of N delta phi over T. So this just gives us, N is 1 in this case, we just have one wire, and so we have BLVT over T. So the induced EMF is just BLV or BVL. And the EMF is induced in what direction? Let's think about it. As this rod moves to the right, the area is increasing, which means that the flux is increasing. There's more B field going through that area, and that is in an upward direction. So the flux is increasing in the, not out of the page direction. The flux is increasing in the out of the page direction, so the current that is generated will oppose that change. So flux is increasing in the out of the page direction, which means that the B field generated by the current will point into the page, which means that current flows around this way in the clockwise direction. So we have current flowing this way. And that current, then if we say this light bulb has resistance R, this is our EMF generated, then we can say that that current is just equal to that EMF over the resistance of the light bulb, because V equals IR, Ohm's law, so that's BVL over R, is the current generated in this loop. So if the current is going that way, then we can see, let me draw that in there, current is headed in this direction. So if we use our right-hand rule, we've got current, B field, going out of the page, which means that there's a magnetic force to the left on that system. And that's our magnetic braking that we've talked about qualitatively. But we can figure out what that is, and we will be able to figure out what that is before too long here. But before we get there, I want to show one more thing, and that is that there's an E field that's generated because an electric field relates to the potential difference. The potential difference, the EMF, our electric field is related to the potential difference like so, and our potential difference is just this EMF, which means this EMF we know is BVL, and that's equal to the electric field times the distance. Well, the distance in this case is, again, the L, the potential difference, is along the length of along the length of this. There's a potential difference across that resistor, and so then the E field generated is related to the magnetic field by just this factor of velocity. So the electric field generated is equal to the magnetic field times velocity. So we have a lot of relationships between the various parameters of this problem. Let's go ahead and do an example of a problem you might do with a situation like this. Handy thing about this video recorder is that you can pause it, so it looks like this text just appears. Anyway, so this is the problem that we're going to look at. I want to find the magnetic force on the rod. It's a B field. It's 0.33 Tesla. The rod is 12 centimeters long, and it moves at 1.2 meters per second. And the light bulb has resistance of 15 ohms. So we want to find the magnetic force. Well, we know magnetic force is ILB, and there's a sine theta thrown in there. But in this case, the current is perpendicular to our B field. The current's going this way, the B field's out of the page, and so the sine theta is going to become sine 90. But we don't know the current yet, but we do know from up here that our current is equal to BVL over R. So our current, that should be a script L, it's BVL over R, and therefore our force, if we plug that in, gives us BVL over R times LB. Our magnetic force is B squared VL squared over R. And once we get there, we can just plug in the values that we have. 0.33 towards our B field, or Tesla, towards a measure of pressure. 1.2 meters per second. Length of 12 centimeters, which is 0.12 meters squared. Pretend that's a squared. My writing got kind of smushed on the edge there. That's 0.12 squared. And then the resistance is 15 ohms. And if you punch that into the calculator, we get a current of 0.33. We get 0.33 squared times 1.2 times 0.12 squared divided by 15. We get a current of 1.254 times 10 to the minus fourth, which will approximate as 1.3 times 10 to the minus fourth amps, which we could also say is 13 milliamps, is the current then generated in that circuit. Now, this force, oh, I'm sorry, that was a force. Newtons, millinewtons. Okay. Now, because we worked out this force was to the left, but I said this thing is moving to the right at a constant velocity. That means that a force to the right is needed to cancel out that force to the left in order to keep the rod moving to the right at a constant velocity. Now, we know that there is a force, and that force has to be equal to the magnetic force. So the force, the power of that pushing force on the wire is, well, work is force times distance, we know, and power is work over time, so we have force times distance over time, which is just force times velocity. And so the power being exerted by the force that's pushing the rod is this force, BVL squared over R times velocity. So that's B squared L squared over R. That is the power being exerted on the rod. However, that's the mechanical power. But when you exert a power, you're doing work, right? And we know that when you do work, you change the energy of something. However, the kinetic energy of the rod is not changing. So where does that energy go? Well, it turns out that mechanical power is converted into power in the light bulb. The electrical power in the light bulb, is I squared R, right? And the current, we know, is BVL over R. So that's B squared L squared over R squared times R. That's B squared L squared over R. And these are exactly the same. So what's happening here is this mechanical work being done on the rod is being converted, or this mechanical energy, the mechanical energy that the rod would get is instead converted into electrical energy. So using this setup in the magnetic field, what we're doing is we're converting mechanical power into electrical power. This is essentially how generators work, and generators that produce basically all the electricity that the whole world uses. So let's do a quick example. Let's say that the light bulb, let me pause and make another. So here's our problem. We have a light bulb that has resistance 15 ohms and it consumes 5.6 watts of power, 5.6 joules per second. The rod is 12 centimeters long and it moves at 1.2 meters per second. I want to find the strength of the magnetic field and the external force required to maintain this speed. Well, what do we have? We have resistance, power, length, velocity. We can't get anything that we're asked to find directly. However, we know that electrical power equals I squared R. So we can find the current in the wire. And the current is just the square root of the power over the resistance. And then once we have the current, we can set that current equal to BVL over R in order to find the B field. So that's equal to BVL over R. And so if we rearrange this, we get that our B field equals square root of power. If we multiply this over, we have resistance over square root of resistance, which is just a root resistance on top, over VL. And then we can plug values in. Our power was 5.6 watts. Our resistance was 15 ohms. Velocity is 1.2. Length is 0.12. And we can stick that into our calculator to get a B field of 63.64. Holy snap, I should have picked different numbers because 64 Tesla is a gigantic B field. But, well, we'll just deal with it for the moment. That's a bigger magnetic field than is realistic. The large B fields they use to levitate frogs are like 14 Tesla. Anyway, and then once we have that B field, we can find the force quite simply by plugging it in. The force, B squared V L squared, so we've got that 63.64 squared times our velocity, 1.2, times our length, 0.12 squared, over the resistance, which is 15 ohms. And I punch that into my calculator, and I get a force of 4.6 repeating, or about 4.7 newtons.